Hello, and welcome to Linear Algebra. This is lecture 7, and our topic today is eigenvectors. Okay, so last time we talked about linear maps. Right? So in this case, if V and W are vector spaces over a field F, then T is a linear map from V to W, if and only if T satisfies two properties, additivity, so T of V1 plus V2 is equal to T of V1 plus T of V2, and homogeneity, T of A times V1, V is equal to A times T of V. Right? And I bring this up because it's convenient to have a concise formulation. You can do this all at one go. Concisely, it's enough to know that T of V1 plus A times V2 is equal to T of V1 plus A times T of V2 for all A in the field and V1, V2 in the vector space. And you can easily check that if you set A equal to 1, then you're checking linearity. And if you set V1 equal to 0, you're checking homogeneity. So you can just check this one equality, and that'll give you both of them at the same time. Okay, and then another thing we did last time, we have our key example. Every matrix, every A, an m by n matrix with entries in F, defines a linear map from Fn to Fm by matrix vector multiplication. Okay, so this time, we're going to talk about eigenvalues and eigenvectors. So these are going to be eigenvalues, eigenvectors of a linear map. So if you've never seen these words before, they can seem a little strange. Eigen comes from German. It means like owned by or the proper. So this you would translate as the proper values and the proper vectors, or the values and vectors of a linear map, owned by a linear map. But in any case, these words are the standard terms used in math. Okay, so the definition is not complicated. If V is a vector space over a field F, and T is a linear map from V to itself, then we say that a vector is an eigenvector of T with eigenvalue lambda, is an element of the field, if two things happen. First, V is not the zero vector, and two, T of V is equal to lambda times V. Okay, so this is the key property we want. T of V is equal to lambda V. So this tells us that the linear transformation acts on this vector in the simplest way, right? It just scales it. It just multiplies it by a scalar lambda. Now, the first property is really important. You don't want to forget that. We're not allowing 0 as an eigenvector. And the reason is that if you were to allow 0 as an eigenvector, then all elements of the field would be eigenvalues, right? Because this equation, if V is equal to 0, just says 0 equals 0, and it doesn't matter what lambda is, right? So we don't want 0 to be an eigenvector because then we're not really getting any information from this equation. Okay, so that's what it means to be an eigenvector or an eigenvalue of a linear map. Matrices are also assigned eigenvalues and eigenvectors. And so what we do here is that if A is a square matrix, square because in order for this equation to hold, T of V to be a multiple of V, then we need V to live both in the domain and the codomain of the linear map. So it has to go from a vector space to itself in order to have any eigenvectors. So same thing, we want the matrix A to define a linear map from a vector space to itself. So it needs to be a square matrix. Okay, so if A is a square matrix, then its eigenvalues and eigenvectors are those of the linear map from Fn to itself given by matrix vector multiplication. Right, so the vector V gets sent to A times the vector V. Okay, when these exist, right, so it turns out you don't always have eigenvalues and eigenvectors, but when you have them, they're wonderful. When these exist, they play a key role in understanding T. So geometrically, what's going on? Geometrically, eigenvectors are those non-zero vectors on which T acts by scalar multiplication. That is to say, T changes their size, but not their direction. Right, so this is geometric. We're thinking of a vector as being given by a length and a direction, right? So T acts on an eigenvector only changing the length, not the direction. However, you have to understand direction as being possibly positive or negative. So you want to think of the whole line in the direction of the vector V. So let's write that down. So though if lambda were to be a negative number, they end up pointing in the opposite direction. So one way of saying that is that they preserve the direction, but not necessarily the orientation. Okay, algebraically, one way of thinking of what are eigenvectors is that these are vectors where T preserves the span. So that is to say, V is an eigenvector for T if V is not 0 and whenever W is a vector in the span of V, then also T of W is in the span of V. Okay. So that's one way of thinking about what it means to be an eigenvector. So eigenvectors are wonderful because they help us understand T. They're also important because they show up in many applications. So I'll give you a few examples at the end of the lecture as a sort of context for this subject. For the moment, let's start by looking at some examples. So diagonal matrices are very easy to understand. And that's because their eigenvalues and eigenvectors are right there. So let's consider an example, a T, a map from R2 to R2. T takes a vector xy and multiplies it by the matrix, diagonal matrix with 1 and 2 on the diagonal. So that's the same as saying it's going to give you back x times 2x and then 2y. Okay, so note that T of the vector 1, 0 is 1, 0, right? So the vector 1, 0 gets sent to a multiple of itself. So we say that E1, vector 1, 0, is an eigenvector of T with eigenvalue 1. Similarly, T of the vector 0, 1 is the vector 0, 2. So the vector E2, right, 0, 1, with coordinates 0 and then 1, is an eigenvector of T with eigenvalue 2. So looking back at the matrix we started with, the eigenvalues ended up being exactly the elements on the diagonal, and the eigenvectors ended up being E1 and E2, right? So you can see how this is going to generalize for an arbitrary diagonal matrix. You have a diagonal matrix, the eigenvalues are the elements on the diagonal, and the eigenvectors, well, you're going to get eigenvectors from the EJ. So every EJ is going to be an eigenvector, right? Whether or not those are all of the eigenvectors depends on what the elements on the diagonal are. But up to taking the span, whenever you have repeated eigenvalues, that's the whole story. Let's look at something that's not diagonal. So let's look at T from R2 to R2. Again, I want it to be given by matrix vector multiplication, but this time let's pick a simple non-diagonal matrix. So just zeros and ones, but let's put the ones off the diagonal. Right? So of course, this acts on a vector xy gives you back the vector yx. Right? So it's just reordering the vertices. Okay, so in this case, maybe you can find the eigenvectors by inspection again, but let's just work things out algebraically. So to find the eigenvectors, we look for non-zero solutions of T of xy equal to lambda xy. So I don't know what lambda is. That's part of the problem. But we want to find lambda, x and y, so that this has a solution and x and y are not both 0. Okay? So, well, the left-hand side here, I can replace with yx. And if I want that to be equal to lambda times xy, that gives me a system of two equations, right? So I want to solve y equal to lambda x equal to lambda y. Okay, now this is a very small system, so it's very simple to just solve it. Let's just solve by substituting the second equation into the first, right? So y, which is lambda x, is equal to lambda times lambda y. So that's lambda squared y. And so moving everything to one side, we get that lambda squared minus 1 times y is equal to 0. Okay, so great. We have two possibilities. Either y is equal to 0 or lambda squared minus 1 is equal to 0. Now, if y is equal to 0, then substituting into this equation, then x is equal to 0, and we are not interested. Right? So that's a perfectly valid solution of the system, but we don't care about that solution. We don't want the 0 vector. Okay, so if you don't have the 0 vector, so if y is not equal to 0, then you have lambda squared minus 1 is equal to 0. So lambda is equal to 1 or lambda is equal to minus 1. Okay, so let's look at those two cases. If lambda is equal to 1, then our system is y equals x and x equal to y. So what we could do is we have xy, and let's just substitute the first equation into here. So instead of y, we can put x, and then we view this as x times 1, 1. So great. So any multiple of 1, 1 works. So we can say here, thus lambda equal to 1 is an eigenvalue with eigenvectors. So we found all of the eigenvectors. It's just x times 1, 1 for any x that's real but not equal to 0. Right? Because of course, if you use 0, then you get the 0 vector, and we don't want that one. Okay, then the other case, if lambda is equal to minus 1, then our system becomes y equals minus x equals minus y. So again, the second equation here is redundant, so we can just keep the first one. And if we substitute that in, that means we're looking at the vectors x, y, where y, instead of x, we keep x, instead of y, we put minus x. So that's x times 1 minus 1. And so just as in the other case, we can say, thus lambda equal to minus 1 is an eigenvalue. With eigenvectors x times 1 minus 1 for every x in the reals not 0. Okay, perfect. So we did that one very algebraically. Let's do one that's entirely geometric. Right, so let's consider t given by reflection across a line in R2. Actually, let's go ahead and call it R, since that's what we've done before. Right, so the picture here, as before, you have this line. This is terrible. Okay, you have this line, you have this vector v, and then you reflect it across the line to get RV. Okay, so geometrically, we're looking for a vector that gets sent to another vector in the same direction, right? Remember, same direction, not necessarily same orientation, but same direction. So we want it to be on the same line through the origin, right? So in the vector I've drawn in the picture, this v, there's the line containing v. Its reflection went to this line, so that is definitely not an eigenvector. It went to a different line. So what is going to be sent to the same line? Well, there's one obvious case, which is if you pick a vector that's already on this line, right, then as long as you don't pick the 0 vector, you found an eigenvector, right? Because if you're on this line, then you're sent to yourself, so you stay on the line, right? So let's write that down. Any v not equal to 0 on the line gets sent to itself, hence is an eigenvector with eigenvalue 1. Okay, but that's not all. The other possibility is if you want this line and this line to coincide, right, the only time that's going to happen is when the vector is perpendicular to the line. Because if the vector is perpendicular to the line, then it gets reflected to just minus itself. Right? So any v not equal to 0 orthogonal to the line gets sent to minus v. Hence, is an eigenvector with eigenvalue -1. Okay, let's do another geometric example. Let's let r sub theta from R2 to R2 be counterclockwise rotation around the origin by an angle theta. Okay, so what does that look like? Well, if you give me some vector v, then I will rotate it. Let's pick the thing. That is r theta of v, that angle is theta. Right, and so every vector just gets rotated this way. Okay, so what are the eigenvectors of this map? Well, we're looking for vectors that get sent to a multiple of themselves. Vectors that get sent, possibly not to the same vector, but to a vector on the same line that you started with, right? Well, that's going to be really hard in this case, right? Because if in the case I've drawn, there's the vector v, well, there's the line containing the vector v in the direction v. And after you rotate, you get this line, right? In fact, no matter what direction you started with, you're going to rotate it and you're going to end up with a different line, unless the rotation was very special. So if theta is not equal to 0 and theta is not equal to pi, then r theta does not have eigenvectors. So here's an example where you don't have eigenvalues and eigenvectors, right? Of course, if theta is equal to 0, if you rotate by 0 degrees, by an angle 0, you're not doing anything. So that's just the identity map. The identity map, every vector that's not 0 is an eigenvector with eigenvalue 1. If theta is equal to pi, then you're just taking a vector and flipping it. So it's just the map v goes to minus v. So then, again, every vector that's not 0 is an eigenvector with eigenvalue -1. So we see for rotations, we have the extreme cases. Either there are no eigenvectors, or every non-zero vector is an eigenvector. Okay, so that's an example of a map, a linear map, that doesn't have any eigenvalues, doesn't have any eigenvectors. What does that look like algebraically? So consider T from R2 to R2, T of xy, 0, 1, -1, 0. Later we'll see that this matrix multiplication is intimately related to rotation by 90 degrees. Right? But right now, let's not worry about that. Let's just take it as an algebraic map. You're just multiplying by this matrix. Here you go. Let's look for eigenvectors. Okay, so if T of xy is equal to lambda xy, right, this is equivalent to having minus yx equal to lambda xy. And that's equivalent to having the system minus y equals lambda x equals lambda y. Right? So again, it's a very simple system, so let's just substitute the second equation into the first one. So we get minus y is equal to lambda times x, but x is equal to lambda y. So we get lambda squared y. And then putting all of the y's on the same side, that gives us lambda squared plus 1 times y is equal to 0. Now, lambda squared plus 1 is not equal to 0, no matter what real number lambda is. So this tells us that y is equal to 0. And then plugging that in here, that tells us that x is equal to 0. Right? So the only vector xy that satisfies this equation is the 0 vector. So we conclude, hence T has no eigenvectors. Okay, now algebraically, there is a way around this, right? Because as I mentioned, there are no real numbers lambda such that lambda squared plus 1 is equal to 0. But if we were working with complex numbers, then we would be able to solve that. So consider the same matrix multiplication map. But as a map between complex vector spaces. Right? So instead of going from R2 to R2, you're going from C2 to C2. So let's give it a different name, S, from C2 to C2. But otherwise, it's the same thing. S of xy is just multiplying by the matrix 0, minus 1, 1, 0. Is xy, which is minus yx. So as before, if S of xy is equal to lambda xy, then lambda squared plus 1 y is equal to 0. But now we can solve this equation by setting lambda equal to I or lambda equal to minus I. Okay, so let's look at these two cases. If lambda is equal to I, then our system is minus I equals Ix and x equals Iy, which is the same as saying, right, so as before, you only need one of these equations, the other one's redundant. So let's keep the first one. It tells us that you can substitute, instead of y, you can put minus Ix. So we get just x times 1 minus I. So lambda equal to y, I is an eigenvalue of S with eigenvectors x times 1 minus I for every x in the complex numbers that's not equal to 0. And similarly, if we set lambda equal to minus I, then our system becomes minus y is equal to minus Ix, x equal to minus Iy. And again, these are redundant. If the first one is true, the second one is true. So we can just keep the first one, and that tells us that we can replace y by I times x. So we just get x times 1i. And so we say lambda equal to minus I is an eigenvalue of S with eigenvectors x times 1i for every x complex number not 0. Okay. Let's do another example. And this time, let's use some of the knowledge we've gained about solving systems of linear equations to find the eigenvalues. Okay, so consider a 2 by 2 matrix. So a linear map from R2 to R2 given by multiplication. Let's go with the matrix 1, 2, 2, 1, xy. Okay, so we want to find if there are eigenvectors, and if so, what are they? So let's solve the system 1, 2, 2, 1, xy equal to lambda times xy. Okay. So if you translate this into a system, and well, let's do that. So the system is x plus 2y equal to lambda x, and then 2x plus y equal to lambda y. And so if I put out everything on the same side, that's 1 minus lambda x plus 2y equal to 0, and then 2x plus 1 minus lambda y equal to 0. So we want to solve this system of linear equations. We know that the way to do it is to form the augmented matrix and then put it into reduced row echelon form. Okay, so in this case, our augmented matrix looks like 1 minus lambda, 2, 2, 1 minus lambda, and then we augment with zeros. Okay, now we want to put this into reduced row echelon form. So we know that what we should do is start with the first row, and we want the first non-zero entry of this row to be 1. Okay, now I have this entry, and the thing is, I don't know at the moment whether or not that's non-zero, right? Because I haven't figured out what lambda is. Lambda might be equal to 1, in which case that's 0. Or lambda might not be equal to 1, in which case it's non-zero. Okay, so we could start by considering different cases, but instead, what we'll do is we'll switch the first 2 rows. All right, that's a perfectly valid row operation. And the advantage is that now I know that it's not 0. I don't have to consider different cases. Okay, great. So now I look at this one. I want it to be equal to 1. So I divide that row by 2. And I don't do anything to this other row. Now, excellent. So my pivot, I've got my pivot. It's a 1. I want to clean up its column. So what I'm going to do is multiply this row by minus 1 minus lambda, and then add it to this row, and that way I'm guaranteed to get rid of that entry, right? So nothing's going to happen to the first row, but I'm going to kill this guy. And let me give myself more space here. I'm going to kill this guy, and then here I'm going to have 2, and then I'm going to add to it, well, let's say I'm going to subtract 1/2 1 minus lambda, and I'm going to multiply this by 1 minus lambda, so minus lambda squared. And then here I have zeros. Okay. Excellent. So let's do this 2 ways. First, let's just stare. Okay. Either this is 0 or it's not 0. Okay. If it is 0, then the matrix is in reduced row echelon form, and we're going to have a free variable. If you have a free variable, that means you have multiple solutions. Okay, that's good. What if this is not 0? Okay, well, if this is not 0, then we're not yet done. We don't have a reduced row echelon form. What we would do is we would divide this row by whatever number this is. Then this would become a 1. Then what we would do is we would have a pivot here, and we would use it to clean up its column. So then we would multiply by whatever we need to make this a 0. And we would end up with a matrix that was 1, 0, 0, 1, right? That's in reduced row echelon form. And here we have a pivot here, and no pivot here. So in that case, we would know that there is a unique solution. Okay, but we don't want the unique solution, right? Because we know one solution of this system is just x and y both equal to 0. We don't want that solution. We want other solutions, right? So what we want is for this to have multiple solutions. And from what we've just seen, that means I need this to be 0. Okay, that's one way of seeing it. So just staring at it. That's perfectly good, but let's just translate this back to a system. And do things a little slower. Okay. So if we translate this back to a system, we're going to get the same conclusion. It's this system. And now we look at the second equation. And just like before, we say, so either this coefficient, 2 minus 1/2, 1 minus lambda squared, is equal to 0, or y is equal to 0. Right? But y equal to 0, so if you plug that into the first equation, y equal to 0 tells you that x is equal to 0, and we're not interested. Right? We're not interested in the 0 vector. Okay. So the only one we're interested in is when this coefficient is equal to 0. 0 is equal to 2 minus 1/2, 1 minus lambda squared. But that's the same. Now here, this you can factor. I'll just tell you what you get. You factor this, you get minus 1/2 lambda minus 3 times lambda plus 1. So lambda is equal to minus 1, or lambda is equal to 3. Right? And of course, this is easy to factor, but because if I pull out a minus 1/2, then this gets replaced with a minus 4, and then I have a difference of squares, and so then it's easy to work out. Okay, so these are our two possibilities. Let's look at each of these in turn. So if lambda is equal to minus 1, then the first equation becomes x equals, no, let's write it out, x plus 1/2, 1 minus 1, 1 minus minus 1 is 2, so that just becomes x plus y is equal to 0. So we're looking at the vectors x, y, where, say, x is equal to minus y, and y is just equal to y, so this is y times minus 1, 1. So these are eigenvectors for y not equal to 0 of t with eigenvalue minus 1. If lambda is equal to 3, then our first equation becomes x plus 1/2, 1 minus 3 is minus 2, so this is just x minus y equals 0. So if we put that into a vector, we have xy, and this says that x is equal to y, so we can just replace x with y. We end up with y times 1, 1. And these are the eigenvectors, as long as y is not equal to 0, of t with eigenvalue 3. Okay, let's do one more example. So I just want to point out that the case of a general 2 by 2 matrix can be treated just as in the previous example. So if t of xy is equal to multiplication by a, b, c, d, then t of xy is equal to lambda xy. This if and only if. So if you write this, well, so this if and only if ax plus by and cx plus dy is equal to lambda times xy. And if we write out the system, that's ax plus by is equal to lambda x, cx plus dy is equal to lambda y. And if we put all of the lambdas on the left side, that says a minus lambda x plus by is equal to 0, and cx plus d minus lambda y is equal to 0. Right, so then the system of equations we're looking at has coefficient matrix a minus lambda, b, c, d minus lambda, and then we'd augment that with 0. And this, if c is not equal to 0, has reduced row echelon form given by 1, 0, and then here you would have 1 over c times d minus lambda, and here you would have a minus lambda times b minus lambda, no, sorry, d minus lambda minus bc. Okay, so then the system will have non-zero solutions precisely when p sub t of lambda, so I'm introducing notation here, this is a minus lambda times d minus lambda minus bc, right? Which if we write that out, that's lambda squared minus a plus d times lambda plus ad minus bc vanishes. Okay, so this polynomial is known as the characteristic polynomial of the 2x2 matrix ABCD, or of the linear map T. The eigenvalues of T are the roots of the characteristic polynomial. Right, and I'll let you check that this is true also when C is equal to 0. Okay, so one thing you can do if you're given a 2x2 matrix is first write down the characteristic polynomial, find the roots of this polynomial, and then go back and try to find eigenvectors for each root. That's fine. On the other hand, that's not the most efficient thing. The method we've been using in the examples of writing down a system of linear equations and then solving that using Gaussian elimination is better in that you also find the vectors, not just the eigenvalues. So you find the eigenvalues and the eigenvectors together, right? Of course, if you find the solutions of the characteristic polynomial, and let's say you're in the case C not equal to 0, then here is the reduced row echelon form, right? This would be 0. So the equation that you're left with is just the one you get from this row. So x plus this coefficient times y is equal to 0. And that's what you would substitute in, just like we did over here. We ended up with that equation, we substituted that in, and that's how we found the vectors, right? Same thing here, we plugged into the equation, we substituted that in, and that's how we found the eigenvectors. So even though this polynomial is nice, and you do end up solving it no matter what, in the 2x2 case, anyway, the method by Gaussian elimination is still a better way of finding eigenvectors and eigenvalues. Okay, so to finish things off, I want to go back and give you some more context. So if you're pressed for time, feel free to stop listening now. Context, I want to tell you a little bit about how eigenvectors in applications. Okay, so I just want to mention quickly 3 applications. So first, the Google PageRank algorithm. So the way Google works, or at least it originally worked, to rank web pages was to give each page a weight, right? This weight is just by how many other pages link to it, right? And then you can imagine having some like random walk where you just go from a given page, you go to another page that by following a link, but you pick a link on the page you're on randomly, right? Randomly with uniform weight. So every link has the same chance that you will pick it as your next move. So imagine you have a process like that that's looking at the internet. And you want to know, okay, what would be the distribution I end up with on all of the web pages, by which I mean, what's the probability that I'm at a given page, given that this is how I traverse the web. And it turns out that the way you do this is you end up with a stochastic matrix, so a matrix where all of the rows and columns add up to 1. And then you're looking for an eigenvector. It turns out that 1 is always an eigenvalue of this, and you're looking for an eigenvector, all of whose entries are positive, and it turns out there exists only one, all of whose entries are positive and add up to 1. Then there exists only one. And that is the probability that the entries of that are the probabilities of being on a given web page. That those tell you what rank to give each web page. It's just the corresponding entry in this eigenvector. That's really cool, and I've put a link on the website. So if you go to my homepage and then find the course webpage and then click on links, I put a link there that explains the Google PageRank algorithm in detail. So that's one place where eigenvalues, eigenvectors show up. Another one I want to mention is principal component analysis. Okay, so imagine that you have a bunch of data, right? And think of your data as like a cloud in some big Euclidean space. And what you want to do is explain the variance in this cloud of data, right? So for example, think that your data forms like some sort of ellipsoid in this abstract space. And what you would want to have are the principal axes, right? Because the main axis would be the axis on which you have the most variance in your cloud of data. So that would tell you that if you want to know where a point is, and you only got to have one piece of information, the best piece of information you could have for finding that point would be what is its value, its projection onto this one major axis, right? And then the next best piece of data would be let's say it would be orthogonal axis. So if you had like an ellipsoid, then it would be the next axis, right? So if you picture a rotated ellipse, then all we're doing is we're trying to find the major axis and then the minor axis. They would be orthogonal to each other, but they might be rotated some. Well, it turns out that these axes are pointing in the directions of eigenvectors. and how much you want to stretch in each direction is exactly the eigenvalue corresponding to that eigenvector, right? So you have this cloud of data. From that, you get what's called the variance covariance matrix. And then you're looking for its eigenvectors and eigenvalues. And the size of the eigenvalues are going to add up to 1. The size of the eigenvalue tells you how much each eigenvector is explaining of the variance in the data. So a million years ago, when I was in college, I used to work at a bank in financial risk management. And I used principal component analysis every day. I had some financial instruments I wanted to value, and so some of them were very complicated, so you couldn't find a formula, so you wanted to do some sort of simulation. You could do simulations that were very costly in computer time, or that were very cheap in computer time. And so what you would do, or what I would do, is you take all of the data that you think is going to influence the price of this asset, you do principal component analysis, and then typically only 2 or 3 components had any real weight. So those you would simulate with the expensive way of simulation, pseudo random sequences. And then the other directions, you would just go with the cheap but quick way of simulating, so Monte Carlo simulation. And then you would use that to figure out what the value of the asset should be. Okay, and then the last application I want to mention where eigenvalues and eigenvectors show up is the emission spectra of isolated molecules. Okay, so as you've probably heard, in physics, it turns out that different elements have different emission spectra. So each element has an emission spectrum, which is like you shine a photon at this thing, and occasionally the frequency will hit an electron in your atom, and it will give it enough energy to go from one quantum level to the next quantum level. So the photon will be absorbed. Or you might have the opposite process where you have some electron going from one quantum level to a smaller quantum level, and so it'll emit a photon at a certain frequency, right? So those frequencies that you can observe are known as the emission spectra. And right, what does this have to do with eigenvalues? Well, it turns out that every molecule, every atom, has an operator associated to it. So you can think of this operator as being an infinite matrix. It sort of is. You have this infinite matrix, and then you could ask about its eigenvalues. And it turns out that the emission spectrum that you're observing is a difference of eigenvalues of this infinite dimensional matrix. So, so there you go. You can see eigenvalues or the difference of eigenvalues in real life. And you know, emission spectrum is how, for example, the element helium was discovered, right? This was in 1868. The spectrum of the sun showed that there was some element that had not been identified on Earth. And so it was named helium after Helios, the Titan in charge of the sun in Greek mythology. And then later it was discovered on Earth and shown to be the same by matching the emission spectrum. Incidentally, the word spectrum here, so it might remind you of something spooky, of ghosts or whatever. That's exactly right. So the word comes from Latin, where it means something hidden, and it started to be used in English in the early 1600s. And by the late 1600s, Newton had used it precisely to describe the spectrum of light, right? Newton famously would shine light through prisms and then see the colors that split up. So it was spooky because, you know, the colors weren't there until the prisms separated them out and you could see them. The word spectrum has since found many uses in mathematics. In particular, when we talk about these operators in infinite dimensions, we don't always talk about eigenvalues, we more generally talk about the spectrum of an operator. And this means the eigenvalues and generalizations of eigenvalues. So we can talk about the spectrum of a matrix or the spectrum of a linear operator. And what we mean are the eigenvalues of that matrix. Excellent. So those are just 3 applications. The eigenvectors and eigenvalues are key for understanding things in general. So any time where you use matrices, linear maps, and you use matrices and linear maps everywhere, you're going to use eigenvalues and eigenvectors to understand what those matrices and linear maps are doing. Okay, so we will stop there and pick it up from there next time.